Yes, in the old-fashioned way. Thank you very much, Merwan, for the introduction. It's a pleasure to be here as usual, and it's a special pleasure for this special event in partnership with Huawei, with which I was glad and proud to be part of several events over the past few years. So this will be a talk explaining part of my research activity in the past 15 years, maybe. I started this like 15 years ago. And there will be a few keywords in common with the previous talk. And we'll explain what. Let me insist that even though I'm not an expert in machine learning, I am a speaker in the next COLT convention that machine learners around you know about, because indeed the subject has some kind of contact points. So this will be about a number of subjects. There will be topics related to gas theory, which is where I was trained originally from my PhD. There will be things related to geometry, so shape of triangles, whatever. There will be things related to economy, and all this will come together in what we will call a synthetic theory of curvature. So let's start by wondering about the distinction between a synthetic and an analytic point of view. And please, in everything that I say, you are perfectly free to interrupt me. So, when do we say that, to explain the distinction, the best is to look at convex functions? How do we define a function to be convex? Well, one simple thing is to say that the second derivative of the function is non-negative, okay? It may be several variables, never mind. And the other way to say that something is convex is to say that phi of 1 minus tx plus ty is bounded above by 1 minus t phi of x plus t phi of y. And this should be for any x, any y, and any t in 0, 1. Okay? Good. So this is one possible definition. This is another possible definition. And we know that if everything is smooth, both are equivalent. This we learn very early. This definition we'll call analytic, because when you do it, you compute some object related to phi, you compute the second derivative, and this gives you another object that you can quantify and use for your computations. This we will call synthetic. It is about a property, geometric property of the graph of phi. It says that phi always lies below the curve which joins the point. This is easy to check. If I give you a function and you want to check the convexity, usually this will never work. If you try to do this, it will be a nightmare. Well, this is simply a thing. On the other hand, this is very useful. A significant part of my life with convex function has been spent using this to check the convexity and using this to prove things derived from that convexity. And second, this obviously is a local property. It is for any x something that you compute which depends only in the neighborhood of x. Well, this is completely non-local. You have to know it for any x, for any y that may be quite far apart. And also, let's say that this is more general than this. You know, imagine that phi is not twice differentiable. Forget about distribution theory, which is more elaborate. This always makes sense, even if your function is something like this, in which case second derivative doesn't work. So this is more general. And also this is more stable. Suppose you have a sequence of functions, phi k, converges to some function phi. And assume that the convergence is a very weak notion of convergence. It will be impossible to pass to the limit in this formulation. While here, it is so easy to pass to the limit. Not even need for uniform convergence. Simple convergence will suffice. that for any point you have convergence of phi k to the limit phi of x, phi k of x to phi of x. So this is very robust, stable notion of convergence, and this shows also why, another aspect of why this is useful. So both have their advantages, and it's like two sides of the same concept. And convexity is so useful partly because we have these two formulations. And it has been, for a long time, a trend to try and develop simultaneously for many topics the synthetic side and the analytic side, both with their advantages and drawbacks. And here it will be about the story with respect to some geometric notions. So, question, how to draw a synthetic notion of curvature? So now what is curvature? Curvature is the main object in non-Euclidean geometry. And curvature tells you about how the lines in a geometry, the lines being the geodesic path, the shortest path, can be compared to the lines in the Euclidean geometry. So, for instance, if I draw something like this, it is a typical picture of positive curvature. This will be flat curvature, zero curvature. This will be a typical picture of negative curvature. So let's put a kappa for a moment as curvature, and we'll give precise definition later. But these are the typical situations. In particular, negative curvature geometry is a geometry in which triangles look like this. And in particular, the sum of the angles is always less than pi, always less than 180 degrees. You can compute curvature in an analytic way, and there is some formula relating the behavior of geodesics to curvature, in which you take twice the differential of the Riemannian metric, things like this. But you can also ask about the synthetic notion of this curvature. And this was developed long ago by people like Cartan, Alexandrov, Toponogov. People in geometry talk of the cat spaces, see Cartan, Alexandrov, Toponogov. And it can be cat spaces for negative curvature, cat spaces for positive curvature. And it is, instead of computing something that we'll call the curvature, we look at properties, geometric properties of the triangles, say. So, by definition, your space is cat plus 0, meaning morally it means curvature is non-negative if triangles are fatter than the flat triangles. What does it mean, fatter? Okay, here is a triangle. To determine if the triangle is fat, I will compare it to the isometric triangle. So this is a triangle in my geometry, a priori non-Euclidean, and this will be the same length, this will be the same length, this will be the same length. Okay? How do I compare and decide that one is fatter than the other? Let's say that it's like you take here the midpoint and you look at the median. And you draw both medians, and if the length of the median here of this triangle is longer, is bigger than the length of the median on the flat case, on the flat situation, then you decide that the triangle is fatter. The mnemo is so easy. If you are a triangle, just take this and assume this is a triangle. Then this is like the tie, which goes from the neck to the middle of the belt. And let's say the less thin you are, the longer should be your tie, so that you are perfectly dressed. So the median is like the tie, and a positively curved space is a space in which triangles have to wear long ties, longer than the homologues, the isometric triangles in the flat space. Okay? So this is a synthetic definition. No computation of whatever, just comparing distances. And again, everything I said here is true. In practice, it is a nightmare to verify this. If I give you a non-Euclidean geometry, you will always go for the formulas that we find in textbooks to check the sign of the curvature. But on the other hand, this is a geometric property that can be useful, that is direct, non-trivial consequence of the curvature, and that will be used in comparison theorems in many respects. Also, this certainly is more general than the curvature definition which we compute a notion of curvature. In particular, take a cone with a point here, you know, some apex, some vertex. The cone is flat everywhere. We know this because we can infer to make the fools with the kids. We can cut a piece of paper, make a cone like a clown hat and put it on our head. So it is flat almost everywhere, but there is a singularity here at this point. It is not a smooth geometry. And you cannot compute the curvature at this point, or it would be infinity. But you can still check the condition here and check that the length of a triangle, that the triangle may be bigger than triangle in the flat geometry. In fact, any triangle, any 3 points that you take here, if the triangle encloses here the point part, then the triangle will be strictly fatter than a triangle which is drawn on a plane geometry. And so the cone is, in this definition, a synthetic space of non-negative curvature. Okay? So it's like a cone would be like the analog of the example I had here for the convex function. And the next thing is, of course, this notion is more stable than the usual definition of curvature in which you take second derivative of the metric. Why? Look, if I have a series of geometries which converges to another geometry, and I want to prove that the limit geometry has the same curvature bounds than the sequence, what do I need to know? Only that the distances converge, the weakest possible notion of convergence of geometry that you may imagine. There's a special formalism, it's called Gromov-Hausdorff topology, but whatever, it is just a way to make convergence so weak that the only thing that matters is convergence of distances. And so it's stable also. So this is also something well known and has been studied over decades by a bunch of geometers. In particular, there is a Russian school and there's a very strong Japanese school also for working in these Alexandrov spaces. So that's the main example of synthetic application of synthetic concepts in geometry so far. Before the lecture, that's the prologue, if you want, of the story that I will tell. So far, so good. Anybody has questions here? Okay. So what I will tell now is the story of the encounter of 4 fields. The first field will be about curvature. And in curvature, there will be the notion of curvature, which I alluded to here, even though I did not give a proper definition. And also we'll talk about the Ricci curvature and geometric consequences. The second topic will be optimal transport, which is a branch of optimization with links to economy, which is also called the Monge-Kantorowicz theory. The third field will be gas theory and statistical physics, with the key notion of entropy in the sense of Boltzmann or Shannon. It's the same formula. Or Kullback in the context of statistics. And the fourth field will be the notion of gradient flow. Gradient flow, which we know as something like x dot is minus grad u of x, if u is a potential, some energy, whatever, like there was in the previous talk, gradient descent. And there's the whole synthetic theory of gradient flows, which has been developed over decades and decades, non-smooth gradient flows, in particular by people such as De Giorgi or Benilan. And I will talk about this in a moment also. And let us say that somehow the problem of finding the proper synthetic definition of Ricci curvature was found by a combination of these four fields. And this combination appeared around 99, 2000, has been developed ever since, is now giving progress, making progress at a very, very fast pace. At the beginning, there was only a couple of papers, including contribution by myself, and now it's growing so fast that I can hardly follow the developments. Let us say that right from the beginning, for me it was like a nice coincidence as I was still PhD student. So I had heard a talk by Felix Otto, German researcher, about his interpretation about gradient flows. Somehow was combining the three topics here. And a few months after hearing, a couple of months I think after hearing his talk, I was reading a course by Michel Ledoux from Toulouse about concentration theory, entropy, and optimal transport at some point. And reading this, I thought first, there are so many keywords that I know that I should be able to say something about this. And second, wow, it has to be related to the talk of Felix, which I heard a couple of months ago. It took me like 15 minutes to find the link, 2 weeks to write the paper together with Felix, and this is my most quoted paper to this day, which shows that the success of a paper is not an increasing function of the time that you put in it. It's a question of having being at the right place in the right moment. Let us continue and explain a little bit about the various concepts. First, let's give a precise definition of curvature, a definition which is good and which we can understand. So let us define the curvature as follows. Sectional curvature. So here is this geometry, okay? It's maybe a curved geometry in several dimensions, and I take a tangent plane in this geometry. 2 directions out of n if it is n-dimensional. Okay, I take a slice in the tangent space. And in this slice, here is a point in my geometry, and I can take velocities going along this slice. And I take 2 of these tangent vectors that I suppose are unit length and orthogonal to each other. This is u, this is v. And I send one geodesic here in the direction of v and one geodesic here in the direction u. These geometers we'll call the exponential map. It's like I send this plane in this direction and this plane in that direction, and because the plane is not full, wants to minimize the amount of energy which is spent, so we'll go around the geodesic. And now you look at the distance between this curve, gamma of t, and this one, gamma tilde of t. And if it was exactly a flat geometry, it would be square root of 2 times t. This is just good old Pythagoras theorem. Okay? But now, because it is curved, there will be a correction. And so at first order, it is 1. The second order vanishes. The third order gives you the corrections. And it is minus kappa over 12 t square multiplied by t, so it's a cubic term. And then the rest is higher order term, as t is close to 0. So this is it, the infinitesimal leading correction which you have to put to the distance of 2 geodesics which spread apart. That's the definition of curvature. It's a definition which is equivalent to the one that Gauss used. And this one has the advantage that it is expressed in terms of distances, so that you immediately see that it's invariant under isometry, the property which Gauss was so proud to discover. So this is a definition of sectional curvature. Why sectional? Well, because I took a section, a plane in the tangent space. Now, this means that we will have a number of curvature. If the dimension of space is 3, say, and I consider 3 directions of my tangent space, there are 3 sections that I can find in this way, either vectors 1, 2, or 1, 3, or 2, 3. here is now another notion of curvature, which is the favorite notion used by people in statistics, in probability theory, in potential theory, in stochastic processes, is the Ricci curvature. So Ricci curvature is an average of these sectional curvatures. So take, this is my point, x, and I take one direction, E. Let's say it's a unit vector. So it's the direction in which I'm looking. And because this is just one dimension among n, let's say the dimension is equal to n, I can complete this with other unit vectors so that this is an orthonormal basis. Okay? And then if I pair E with either E2 or E3 or whatever, this gives me n-1 possible sections. And I will add up all the sectional curvatures corresponding to this. So Ricci in the direction E is by definition the sum of the curvature associated with the sections E, Ej, for j going from 2 to n. That's the definition equivalent to the definition used by Ricci. It turns out, and it's a non-trivial fact, that this Ricci, which you see, to every unit vector it associates a number, in fact you can extend it into a quadratic form on the tangent space. So that's a quadratic form. It is famous that Ricci curvature is the right notion of curvature to use in general relativity, and so it played a cornerstone in the work of Einstein in general relativity. It is also famous that to this date, general relativity had only one, let's say, application in practical life, which we all know is GPS, because when you want to compare the times which the information which is sent by satellites to you, you have to take into account the fact that the time is not exactly the same for these signals which travel at very fast speed, and the relativistic correction is one of the corrections that you have to take into account. Otherwise, you just miss the point. But let's say, I think it was computed if without the general relativity correction, your GPS would be in error of 10 kilometers after 1 day, something like this. So it's an error you have to take. The Ricci curvature is the one that gives you the information about the distortion of space-time. What to say next about Ricci curvature? Ricci curvature, as I said, is the notion of curvature that everybody interested in probability and measure likes. It goes well with measure. Why does it go well with measure? Because while the sectional curvature tells us something about distance, the Ricci curvature tells us something about volumes. And you know, we are taking an average of distances in various directions. It's a bit like a surface. So I will give you another interpretation of the Ricci curvature. And before that, let us say that, for instance, if you're a specialist of diffusion processes and in your geometry you start a Brownian motion, and we know in general there is this correspondence between solutions of diffusion processes like heat equation and the Brownian motion that was discovered by Einstein, Bachelier, and others. And you may ask, does this remain true in non-Euclidean geometry? Answer, yes, if the Ricci curvature does not blow down too fast, does not go too fast to minus infinity. If you have a lower bound on Ricci curvature, that is, things don't get too negative in curvature-wise, then you still have your correspondence between the stochastic processes and the partial differential equations. Please interrupt me if I am going too fast or too slow. So here is an interpretation about Ricci curvature, the one that you can explain to anybody. So it's an informal interpretation. Yes. Here, this is me standing and observing some light source which is here. Okay? This is the light source. the light travels in space in all kinds of directions around geodesics. But if I'm interested that those light rays which arrive to me, it looks something like this. Okay? And it may be distorted so that you see this is what you get. The geodesics are not straight. And so if you are here and asking, what do I see? The impression, the visual impression that you have depends only on the slopes of these, the directions of these rays when they arrive on you. And so if you try to reconstruct the image from observation, this will be your impression, you see? And here, this is a typical picture of positive curvature, meaning that you will overestimate the size of the source. Overestimate in which sense? If the context is this, positive sectional curvature, you will overestimate, say, the diameter of the source. If it is Ricci, what you will overestimate is the surface of the source, or the volume. You'll have the impression, for instance, it will be something like this in reality, and your impression will be something like this. It may be smaller in some directions, larger in other directions. But if the apparent surface is larger than the true surface, and if that is always the case, it means your space is non-negative Ricci. True surface. And if it is like this is a Ricci positive. And there are similar ways to formulate Ricci bounded by minus 1, minus identity, Ricci bounded by minus something. I said it's a quadratic form, so you should compare it to other quadratic forms. Okay, so far so good. Let me mention also that this is the thing that people love. So probabilists will say, okay, take a manifold. Let's assume that Ricci is bounded below on all the space so that I know that there is no blow up of my Brownian motion and things like this. Let me also notice that nobody works under assumptions of negative Ricci curvature. It makes sense, but it's not useful. There are no theorems about it. And there are deep reasons why it's not interesting to consider negative Ricci curvature. While negative sectional curvature, there are a bunch of people who work with this, and it's very important in certain branches of mathematics. But for Ricci, when you talk about Ricci comparisons, it's always compare Ricci from below. Okay, so far for the story of curvature. And let's go on with this other story here, optimal transport. So Gaspard Monge here was a remarkable mathematician of the 18th century. He was a personal friend of Napoleon, and he was a devout revolutionary guy, you know. He was one of the founders of the École Polytechnique, École Normale Supérieure, and so on. And very well known for his geometric intuition. So this is the problem that Monge asked in a memoir which appeared around 1781. Imagine that you have some piece of whatever, of soil or whatever. Maybe it's, let's draw it rather in this way. Suppose that you have some matter, something that you are extracting from the ground. You see, this is a mine of whatever. And you want to transport this and rearrange this in some way. So this will be some kind of construction that you have to make. Okay, good. And each piece of the matter you transport here from some point x, you will transport at some other point, say t of x here. Here it's a one-dimensional drawing, but in reality, x may be 3 dimensions or even more, and so t of x also will have 3 components or even more. And of course, in general, there are many, many ways for a suitable map T, which rearranges your matter from the starting condition to the final condition. People will call this an operation of push forward. If I consider at the mass here as a measure, probability measure maybe, and I call it mu, and here I call this nu, the distribution of matter, then the condition is that the push forward of mu by t is equal to nu. But this really means that I transport every atom of mass, which was at position x, to the destination T of x, and I look at the shape of the resulting transform distribution after this transport operation. Okay? And so Monge asked, okay, there are infinitely many ways to do it. Good. But certainly they are not all equal, and there has to be some ways which are better than others. And he asked how to find the optimal way to do this. It can be a very practical issue. For instance, assume you own a big taxi company. You have 30 cars. At the end of the day, they should go back to 30 parking lot places. How do you decide which car goes to which parking lot? It's again a problem of transporting the matter. In here, every atom corresponds to one taxi, and you want to make sure that in the end, every parking lot place has a taxi in there. But how to decide that this one goes there, this one goes there? You want to spend as little fuel and time as possible. So here is what Monge said. Let us minimize. It's just putting this into mathematical formula. The integral of the cost to go from x to T of x, and this here will be a cost function, and I integrate this according to the starting distribution. And the minimum is over all t such that the image measure of mu is equal to nu, which means at the end of the day, I have rearranged the matter as I want it to. So this is the Monge problem. Okay. And this is a dreadful problem because, of course, depending on your, if you look in terms of t, it may be a non-convex problem, of course. This cos c here may be anything. Monge was taking the distance cost function, which is degenerately convex. But even more serious, this condition is highly non-convex. So you are facing a highly non-convex optimization problem. If you try minimizing, it doesn't work, doesn't pass to the limit anyway. Still, Monge managed to make interesting observations about the geometry of the solution, if it exists. It took more than, it took nearly 300, I'm exaggerating, it took 220 years before people could prove that the problem of Monge had a solution in general. Monge was assuming solution exists and drawing conclusions. Proving that the solution always exists was a very tricky variational problem. Kantorovich is a completely different profile. Even though there are some common points between both, one fun coincidence being that both of them were extremely precocious students, and both of them were professors at the age of 22. So Kantorovich, a bit of praise for Kantorovich, one of the great mathematical economists, actually Nobel Prize in economics in the 70s, one of the first masters of computation and numerical analysis, let us say. He played a role in the war as applied mathematician in some very sensitive matters. He was involved in the development of the atomic bomb on the Russian side. He was also involved in the improvement of the taxi fare in Moscow, so working on all kinds of problems, and at the same time a master in abstract functional analysis. So Kantorovich at some point gets interested in this problem without knowing about the work of Monge and reformulates this in the following way. Minimize the double integral of c of xy pi of dx dy, where c is still the cost function, and the minimum is taken over all admissible pi, which have marginals mu and nu. So this pi here is a joint probability measure, such that when you integrate over x pi, so it gives you a measure in only y, and you will obtain mu of dy, and when you integrate in y, you will obtain mu of dx. Okay? So if you have an engineer heart, it is very easy. This is x, this is y. You have some joint probability measure, which is like a blob here. And when you take the average here, you obtain the measure nu. The average there, you obtain the measure, sorry, this is mu, and this is nu. And the amount of intensity here tells you how much mass you should transfer from position x to position y. It's really like reading on the plan. And these people call a transportation plan. So that's the problem of Kantorovich, and it's the same problem as Monge, except that it's a probabilistic way to formulate. A point, some matter which is at x, may be spread. Half will go here, half will go there. It's a probabilistic version of the Monge problem. And Kantorovich discovers several things. First, this problem now is perfectly convex. Convex constraint, and convex here, whatever c, this is a linear function of pi. Actually, it is a linear programming problem, meaning that the constraint is defined by linear inequalities, and what you want to optimize is also linear in the unknown. And Kantorovich is actually one of the fathers of linear programming. It is funny that in the days of Soviet Russia, some of the theorems of Kantorovich were considered so seditious that it was forbidden to mention them in public. And nowadays, the work of Kantorovich is everywhere. People learn about it in microeconomics courses and so on. So what, for instance, what did Kantorovich prove about this? It's called the Kantorovich duality. And by stating it, we shall understand why it was relating with economics. So the Kantorovich duality. It will not tell you what is the optimizer, but it will tell you if an optimizer exists, any optimizer satisfies a certain property and can be re-expressed in terms of optimal prices. So minimum of double integral c of xy pi of dx dy is equal to the supremum of integral phi d nu minus integral psi d mu, where here pi has marginals mu and nu, and here phi psi are real valued functions, such that phi of y minus psi of x is always bounded above by c of xy. Okay. What is so seditious in this? So here is the interpretation, the shipper's interpretation. Assume you are here, the big boss, trying to organize how to send the production. I told about taxis. Maybe it is something that you produce in some, you extract from some mine and send it to some facility where it will be bought or whatever. Transport it from producer to consumer. And this is your problem, how to organize the transport. And then this other guy comes to me and says, look, I'm specialized in transport. Don't worry. Let me buy the good from you, from your mine. I will buy it, and then I will sell it back to you at the consumption site. And in between, I do the transport. I am not a crook. So you can check that whatever the final destination y and the start point x, I will not charge you more than the transport cost. And then it's up to me to organize the transport. Of course, this is what in the end of the day will be in the pocket of this guy, what he will have earned by selling back and buying at the initial time. And of course, if he wants to maximize his profit, this is what he should achieve. And the Kantorovich theorem tells you it's the same for you to minimize as somebody with an arc view the transport, or for that guy to maximize his profit. And this was considered a very capitalistic theorem, you know. Actually, Kantorovich wanted to build a rational theory of prices, which almost certainly was going to death sentence if it had not been for him being so useful in other projects. In those days, you know, building a rational theory of prices was considered like counter-revolutionary. So Kantorovich started this and gave ways to to study the solution. Now the subject was revolutionized at the end of the 80s with independent works. End of the 80s, independent works by Brenier showing some relation of this problem to fluid mechanics, by Mike Cullen showing relation to problems of meteorology, and with John Mather showing relation to problems of dynamical systems. And then many people jumped in and proved theorems. Let us just give one theorem. So if you are in geometry and you consider natural cost function to be the square of the distance between 2 points. Why the square? Well, if you are in physics, kinetic energy is with the square of the velocity. And if you look at the energy which is spent, squares naturally appear. Also in the previous talks, there were natural squares as error functions. It's a natural way to define error which has all properties. So let's take this. How does it look like, the optimal transport? Using the theory of Kantorovich, using a bunch of convex analysis, quasi-convex analysis, whatever, not quasi-convex, semi-convex, you find that the optimal has the following shape. T of x, so that's your optimal transport, is equal to exponential grad psi of x. This means what? I start from x, I send from x geodesic with initial velocity grad psi of x, where psi is some price function, as in that duality theorem, and I go for time t equals 1, and then I stop. And that's my t of x. And such that psi is d square over 2 convex, meaning it has some kind of convexity property. There exists some function zeta of y, real valued, such that psi of x is equal to the supremum of zeta of y minus d of xy square over 2. So here it is. Whenever you have a map which takes this form, exponential of grad psi of x, and the geodesic going from x to exponential grad psi of x is minimizing geodesic, then you know that it is a solution of the Morse problem, and it is optimal if you are performing transport in a non-Euclidean geometry with cost which is a distance square. This is a theorem due to McCann, Robert McCann. Okay. Hey, so many things to digest in such little time. So far, so good? Okay, so basics of optimal transport. We talked about this, we talked about this. Let's be so brief about this by just giving definitions. One possible definition. How do you define gradient flow in a non-smooth setting? Well, you always do, no, not always, but the simplest way is to do some kind of time discretization. Time discretization. So fix a time step, tau, very, very small, and you construct x0 tau, x1 tau, etc., xk tau as your discrete approximation, meaning that this should be something like x of k tau. And at the end, you will send tau to 0, and your discrete approximation will become a continuous limit. And at each step, if you have constructed k tau, then xk plus 1 tau is obtained as a solution of the minimizing problem u, my energy, u of x, plus distance x xk tau square divided by 2 tau. Meaning I want to make you decrease as much as possible, this is gradient flow, but not going too far from the point where I was just a moment ago. Not going too far, and how is too far is you look in terms of the square distance divided by tau. If you pass to the limit, you obtain the gradient flow, but of course, this makes sense even if there is no gradient, no smoothness, just a metric space is enough to make sense of some of this. In general, however, it will not converge to a single defined object. Maybe there are many possible limits, and that's the problem. How can you define a gradient flow which is unique, which is well defined in the limit? It was developed in particular by De Giorgi in order to do theory of image processing. How do we do gradient flows on objects so complex as shapes, for instance? And let's say no more about it. And let's concentrate in the end about this, entropy, Boltzmann. So entropy, it may be argued, is the cornerstone of both statistical physics and information theory. And in entropy, we know that this is the famous Boltzmann formula. S is k log W, in which W is everything that you cannot know about your statistical system. For instance, if you are looking at the air, you can measure pressure, you can measure wind, you can measure temperature, you can measure density, but you will never know what are the actual positions and velocities of the particles. So all this is the unknown. W, it may be a set of high cardinality, or it may be a continuous set, and the volume will be important. You take the volume and multiply by some constant. And as Boltzmann understood, you can always find a practical formula for this in terms of the density F. And it has been formalized in statistics under the name of Sanoff theorem. It's the rate of deviation for the empirical measure in technical words, but it's also a simple exercise which corresponds to the following. Suppose that you ask, which is the number of ways to put n particles in k boxes such that, think of each of these boxes as a discretization of the state of one particle, say position and velocity, such that for box number k, the number of particles in the box k divided by the total number of particles is approximately equal, that is in the limit of many particles, to a fixed fk, which is given, and which is a frequency. So you are asked, in other words, knowing about the distribution of particles, the statistical distribution of particles, which is this, how many ways are there to realize this in terms of many particles that I will spread along? And the answer is that if you look at 1 over n log of this number of ways to achieve this, to achieve these fk's, and you go to the limit n goes to infinity, you obtain minus sum of fj log fj over j, giving the famous x log x typical nonlinearity which appears in the Boltzmann entropy and is the same that you find in the Shannon entropy. Whence S equals minus double integral of f log f. Well, integral over all the space. Very often one speaks of information rather than entropy. So the formula for information would be integral of f log f. And very often it is with respect to some measure. And here this measure may be uniform measure if you're in the context of classical statistical measure, or it can be some reference measure which is arbitrary. Okay. Maybe it is, if you are a geometer, it will be the volume measure in your geometry. Maybe if you are working in a problem with a potential coming from physics, you will consider the Gibbs potential, something like exponential minus v of x dx. Many possibilities, but you may be interested in counting the entropy with respect to a measure which is non-uniform. And what do we do with this? So first, there is a clear statistical interpretation. Entropy tells you if a given statistical distribution is rare or very common. And it is the information here that will tell you if it is very common. To have something that is very common is when this h will be as low as possible. Entropy as high as possible. And also it's classical that in many respects, when you look at distributions of the maximum of entropy, you will have Gibbs distributions, you will have Gaussian distributions, and this plays a major role in statistical physics in equilibrium. Just to quote a few places in which entropy was used in an important way. For instance, since it was a question about the empirical measure in the previous talk, so throw in particles x1, etc., xn, which are IID and low nu. Okay? And you write the empirical measure. Mu hat is 1 over n sum of Dirac masses at xi. Okay? And we know by law of large numbers, in the long run, this will be an approximation of nu. But which is the probability that I make a mistake? Probability that the empirical measure looks like something than a certain mu rather than nu. What's the probability that I miss the target by reconstructing? Well, it is approximately exponential minus n h nu of mu, which is the relative information of mu with respect to nu. So this shows you that it gives you a measure of discrepancy of one measure with respect to another. And as such, it also plays major role in statistics, where it is called often Kullback information. Another example of a place in which the entropy is useful, it was used in John Nash's masterpiece on the regularity of diffusion processes. It was also used to give quantitative errors in the central limit theorems. You may think that central limit theorem is, most of us, when we see this in computations, in teaching, is that central limit theorem is related to Fourier analysis. You take Fourier transform, you look at this, etc. But there is a much more beautiful proof going through entropy, in which the Gaussian distribution arises because it is a distribution of maximum entropy for fixed variance. So these are some of the examples. Entropy was also used by Grigory Perelman in his proof of the Poincaré conjecture. It's kind of ubiquitous. So here we are now. I have 0 minute left to tell about the core of the talk, so I will, in a very rude way, take a few minutes with the authorization of our big boss, Emmanuel. And what is the link between all of this? Was discovered around the end of the 90s that there is a strong link between them, and this was done in a seminal paper by Jordan, Kinderlehrer, and Otto. Which is the link? I will tell it in words. If you consider probability measures on some geometric space, and you know to transport one measure on the other has a certain cost, so there is a transport problem. This transport problem gives you a distance on the probability measures. So you will have a certain distance. Let's take cost to be the square of the distance. And let's take the square root of the cost as a distance on probability measures. So distance between mu and nu being the square root of the optimal cost, with cost c equals d squared of transport cost. So this gives me a metric space. I can apply then the gradient flow procedure with that distance between probability measures. I need an energy function on probability measures. I need two things. I need a distance and I need an energy. Let's take this as the energy, the entropy. And so let's take something, or the information if you want. So let's construct the gradient flow that will minimize the descent for the information. Question, what do you get? Not obvious answer, heat equation. And this is a very general procedure. So heat equation is the gradient flow of the information H for the optimal transport metric. This was a discovery of Jordan, Kinderlehrer, Otto. And you know, first they did this in Euclidean space, but then people did it in a Riemannian context. Now even in discrete settings, it's an extremely general rule. And the second link was between these three objects. And this was a paper of myself with Felix Otto. And we showed that also there is a very simple link between these three. And the link is this. If I want to know what is the Ricci curvature, in a way that is remindful of this, but without any issues about directions or whatever, in a way which is robust, in a synthetic way, I need to look how the entropy is changed in the process of optimal transporting one distribution onto the other. And this is the criterion which later, starting from 2004, was built into a synthetic definition of the Ricci curvature and used to prove a number of theorems. So let me show you a definition. And you will here have the real meeting point of these three fields. How do we define that a certain geometry with maybe no smoothness has a Ricci curvature, let's say, bounded from below by 0, synthetic. So this was turned into proper definition in works by Lott and myself, plus Karl Theodor Sturm, and now is often called LSV spaces. You had CAT for sectional, LSV is for Ricci. So how do you do it? Take any probability measure, starting probability measure, mu0, and final probability measure, mu1. Assume that this is the initial state of your gas, this is the final state of the gas. I call this the lazy gas experiment. You are giving an order to the gas, you have just 1 minute, t equals 0, t equals 1. After time 1, it has to be in this shape. And the gas is free to rearrange how he pleases. So maybe particles will go this way, that way, etc. And the gas will choose a way which will spend the least amount of kinetic energy. An optimal transport way, because he's lazy. This is life. But there is a fixed target which you impose. And during this process, what is interesting for you? You know, it's all this question about surface, apparent surface, so you will try to measure the spreading of the gas. Maybe at times the gas will be very much compressed. At other times the gas will be very much spread. So we need a measure of how much the gas is spread. And the right notion of measure to do this is this. The entropy as a measure of the spreading of the gas. So you will measure the entropy of the gas at each time. From t equals 0 to t equals 1, if the entropy curve is a concave function of time, it means, if it is always a concave function of time, it means that Ricci is non-negative. It's equivalent to S equals minus integral f log f. Let's say, I will write this. It's not very clean, but mu t log mu t, where mu t is the evolution at time t of the gas, is a concave function of t. And this, at first, looks like a complicated definition. But look, here there is no need for any smoothness. It uses only robust objects, integrals, minimization of cost function. It's a convex optimization problem which is behind, so we know it should be very robust. And indeed, this notion of synthetic curvature, what can we say about it? And so it took a bunch of people to show that this notion of Ricci first is compatible with the Cartan-Alexandrov-Toponogov theory, is more general than the classical one, allows to prove many geometric theorems, sometimes under slight reinforcements of the structure condition. Is enough to define a unique gradient flow, a unique heat equation. So if you have a space which is as horrible as you may imagine, you know nothing about how wild it is, whatever. If you know that Ricci is bounded from below in this sense, then you know it has a unique heat flow on it, and you can do some calculus in it. It's in general nonlinear, this heat flow, but if you impose an extra Hilbert space condition on the Sobolev space, anyway, some extra condition, it becomes a linear flow. One example of something which truly captures the meaning of curvature and which is emblematic. Example, the Brun-Minkowski inequality. Deep and simple. If I have Ricci bounded below by 0, and I take a compact set X and a compact set Y, and I look at all midpoints, so I draw all possible geodesics between one point here and one point there, and I take the midpoints each time. And this gives me a set of midpoints. Then this set of midpoints cannot be small. It has to be large. The volume of midpoints of X and Y to the power 1 over n, effective dimension of the space, is bounded below by half of the volume of X to the power 1 over n plus volume of Y to the 1 over n. So that's one example. There are many others. Other applications, and here we will be closer also to the spirit of the previous talk. So Ricci bounds also imply bounds on the convergence of gradient flow. It was recalled past talk. If you have a uniformly convex function, then you look at the gradient flow in there, the convergence is exponentially fast. You can see this as a geometric property. And the condition, in fact, is Ricci bounded below by a positive number. This corresponds to exponential convergence in a natural way. They also imply concentration measure bounds, concentration of measure. like something like if you look at the error between observed quantity 1 over n sum of f of xi, where these are iid, this will be approximately equal to integral f d mu, and the convergence will be exponential if you have positive Ricci curvature. So again, in approximation theory, say strictly positive Ricci bounds. And so on. So many things that you know for the smooth Ricci case also extend to non-smooth Ricci case, and you can also prove inequalities. Quite recently were proven using this definition, inequalities, isoperimetric inequalities, which are sharp outside the range of Riemannian geometry, Finsler type geometry, which were quite a surprise. Also, there is a possibility of discretizing. A bunch of people have looked at this, including Jan Olivier, Jan Maas, Matthias Erbach, and a bunch of others. What does it mean? We all know life is discrete in computers and in many cases, and you will say it's good to have a continuous geometry, but in real life it may be a bunch of points. And then maybe all these ideas of curvature and so on will collapse when you have points. Indeed, geodesics don't exist in a discrete space. But you can always find approximate geodesics. And you can, massage a bit the definition. I erased the definition, which was a mistake. But a measure always makes sense in a discrete space. Instead of minimizing over paths which are time continuous, maybe they are approximately continuous and there will be some small error that you can justify. And this was studied. In particular, we know precisely now what it means for simple test case. Take -1 or 0,1 to the power n. So this is discrete hypercube. How is it curved depending on n? It looks like an absurd question, but it is not. If you have in mind that there will be some geometric inequalities with some taste of curvature that will allow you to prove isometric inequalities inside this, or spectral gap inequalities, or things like this. And this is indeed what was achieved. So this exact question was asked by Dan Struck at the end of the 90s. What is this curvature of the discrete hypercube? And now, thanks to the works of these people and this kind of definition, we know. In particular for this, the answer is 1 over n in some sense. At least that's the order of magnitude. So it acts like a space of positive curvature. Means you will have convergence of gradient flows, you will have concentration of measure, etc. And the bound is less and less as n goes to infinity, and the decay is exactly like 1 over n. So this was one of the motivations. A final remark just for those who are interested in the star theorems. Part of the proof of Grigori Perelman on the Poincaré conjecture, I see just part of it, was rewritten using this mixture of entropy, gradient flow, curvature, and optimal transport. This was done by John Lott and Peter Topping. Okay, that's it. Thank you.
Are there questions?
Now is the worst time for questions just before the lunch.
I have just a question in the Simon-Kontorovich theorem. I mean, I saw some paper applying this to telecommunication where they wanted to transport on the optimal placement of base stations up to some cost.
Yes, absolutely.
Of pushing and where you can put them on the
I remember discussing this with people from telecom. Yes.
You're also discussing with them.
Yes.
Okay.
I was in discussion with some of them.
And one of the problems when I saw those papers was in the implementation, because the formulation is nice, but is there like some software or techniques?
Oh yes, in particular the recent PhD of, who was his name? He was my student in INS long ago. there is a recent PhD, Quentin Mérigot. The PhD of Quentin Mérigot gives very convincing, fast algorithms which allow to solve the problem in a very fast way. That is, in particular, when you have image processing problem. Also, it's a typical problem of image processing. You want to, you have some image and you want to match it with another. For instance, you have two different images of the same object, one with a certain palette of colors and the other with a different one, and you want to match, adapt the colors here so that for this it's okay. Maybe for stereoscopic vision, you know, you have to adapt. So you have to match the two pictures. You have to solve an optimal transport problem on one, and optimal transport is one of the ways. And with the recent computational progress, they can do this in time, which is perfectly adapted for that purposes. So I would guess also with this. The thesis is really good.
Other questions? Yeah.
Can you talk about space with negative Ricci? Why they are?
Okay. First, if you go deep into the working heart of the equations, I will write. How do you, in practice, do the computations? Is like you would be interested in the Jacobian determinant of exponential map with a certain grad psi. Let's take a gradient initial velocity for our vector field, like in the problem of Kantorovich, but it's also the way they formulate it usually. So I have in this direction, this direction, this direction, and I send bunch of geodesics. And I ask, how is the Jacobian determinant of this, or are volumes distorted? And you solve this. And let's call this J of t, for instance. Okay. And you go into this and you try to find an equation, and you will find that the corresponding equation is something like J of t to the power 1 over n, second derivative, plus Ricci at the point that you are considering, multiplied by J of t to the power 1 over n, is bounded above by 0. This is a way to translate infinitesimally the Ricci curvature. And it's a way like I want to know how the volume of particles evolves. If I am a specialist of fluid mechanics, I will say this is like a flow with the velocity which is potential field. And I am interested in how density will increase or decrease along the flow. The variations of the density are given by the Jacobian determinant. And there is this differential equation, linear, which appears. And there is a sign here. And if you want to do it without a sign, you are dead, because somewhere in there is, you know, it's an equation which is not closed, because there is a trace operation, as always, when you differentiate Jacobian determinant and a square. And trace and square don't commute, but they commute up to 1 over n coming from Cauchy-Schwarz. But there is an inequality, and the inequality goes into this direction. There is an equivalent formulation. If you discuss with geometers, they will tell you Borchner formula. People in geometric analysis, they say, how do we detect Ricci? It's always in this way, by comparing minus grad psi, grad Laplace psi, plus Laplace grad psi square over 2, and looking what it is, and this will be bounded below by Ricci times grad psi square plus Laplace psi square divided by n, the dimension. And in this term here, there is again a Cauchy-Schwarz inequality, because you are comparing this to the full Hessian of psi norm square. Okay? Between this and this, there is a 1 over n which comes, and there is an inequality. And if you want to have a closed equation with Laplace and so on, you need this inequality. So at the level of equations, that's the reason why you always need the inequality. There is a Cauchy-Schwarz which gives you inequality, and without the Cauchy-Schwarz, things don't close up. This is called the Borchner formula. Now, people have shown some strong theorems about negative Ricci curvature, saying that, for instance, there is no geometric consequence of Ricci curvature bounded above. And for instance, you can have a family of spaces with negative Ricci curvature converging in the sense that distances converge to a space with positive Ricci curvature. So that all the geometric properties that you can imagine that would be characteristic of negative curvature are not stable. They don't make sense. There are some analytic consequences which you can look at by looking at solutions of heat equation, for instance. But they don't translate into any good geometric properties. Emmanuel.
Somehow, all the questions interesting in the negative when you're in the negative curvature case or not. And I mean, you're somehow saying that you're dead when you just try to solve the problem in negative curvature. But is the question interesting, first of all? And second, I mean, I'm always working in negative curvature, so in general it's very rigid. That's why you won't have to look to convergence problem. You have single objects and you cannot deform them. But, so it's other type of questions. So
it is other type of questions, but first, indeed, I say the people in dynamical systems, for instance, are very fond of negative curvature. But it's always a sectional negative curvature. It's neither a negative Ricci curvature. So, right?
bisectional negative curvature.
Bisectional also, yes, absolutely, yes. It's sectional or bisectional, but it will never be the Ricci or the analog in the context of the complex case, in the Kählerian case. The Ricci case is really one that comes with a sign that is in some sense given, and it's a lower bound below. And even at level of finding the propagation of local criterion to global criterion, for instance, works fine with negative sectional, with positive sectional, and with positive Ricci, but these are the only 3 cases in which this works fine. There is, apart from that, there is not strong motivation for this. People in concentration of measure are interested in knowing that the measure concentrates so that your space looks like bounded, and also that's a typical philosophy of positive curvature. Like in the Bonnet-Meyer theorem type, positive Ricci curvature shows that the space is small in a sense. Gaussian space is a concentrated space, is also positive curvature case, and so on. So there are no real motivation that I can see about a negative Ricci. Negative sectional for sure is very important. And by the way, the most general case for good concentration of measure is when the target space has positive Ricci curvature, but the start space has negative sectional curvature. So it's only the space in which you put the observation measure for which this Ricci bounded below assumption makes sense. I see observation measure, it's always, if you remember the interpretation of Boltzmann entropy, it's always about observing data in the end. You put the measure, you want to know how they look like and so on. There, you want the Ricci. Ricci positive, you can also say, is a way to make sure that errors don't matter too much. Even if there is a small error, it will look kind of the same and solution will automatically be where it should be. Negative curvature, we know it's chaotic, all kinds of crazy behavior can occur and so on.
Okay, maybe two small questions. One is your title. So you had triangles like.
Oh gosh,
men.
yes,
Men.
yes, men. Because in this case, this I often give a popular broad audience version of this talk in which I forget about the equations and so on. The men is because this is an encounter between fields, but was only made possible by an encounter between people. At some point, I met Felix Otto. It was some accident, and this resulted in these domains coming together. At some other point, I met John Lott, and this was the start of the theory. So we should always, because it's a story of meeting of fields, but it's always stories of meeting of human people behind this. And that's the raison d'être of institutions such as Institut Poincaré or Institut d'études scientifiques or the whole conglomerate Carmin that we are part of. Make people meet so that the new ideas can come together. mathematical theories, in the end, they are abstract objects. But at first, they are people talking to people.
Okay. And the second question, very fast, remedial fields is related to which part?
No. It's for different. The field medal was only in the statistical physics, but not for this work. It was related to issues about the rate of increase of entropy in a gas and the solution of the theoretical problem of Landau damping, which is you take a plasma, you start from your plasma at equilibrium, so you take the plasma as a bunch of electrons. The evolution equation will be the so-called Vlasov equation. It's like Boltzmann, but with no collisions, electrostatic interaction. You make a small disturbance, electric disturbance, and you want to know if your electric field will decay spontaneously. It's like decay without collisions. And in some respects, this looks very paradoxical. And together with Clément Mouot, we showed that indeed this is true under technical assumption of periodic boundary conditions and for very smooth data, smoother than C infinity. It's a Gevrey regularity. And we explained why. And in particular, we showed that this problem was related to other problems of theoretical physics. It was a big discovery for me. And this problem later was the basis for solving a problem in fluid mechanics, which was standing for more than 100 years. I will explain it in words also. It was done by Bedrosian Masmoudi. Beautiful paper taking inspiration from our work. Take a fluid, two-dimensional, so like on this wall, and take it a shear flow, and take a linear shear flow. So this is x, this is y, and I will draw the vector field of the fluid. So like this. Okay. So horizontal vector field and proportional to the height. And then you make a small disturbance of the fluid. And then you wait, and you assume that your fluid is non-viscous and incompressible. Simplest in some sense. And you ask, is it true that just by the fluid equations, it will converge to another rest state in which the velocity is horizontal in large time? And this problem looks simple, but it's horribly difficult to solve. And it was solved a couple of years ago by Bedrosian and Masmoudi using some of the ideas we developed with Clément Mouot. So this other set of works related to evolution equation in mathematical physics is the one for which I got the medal.
And it's not your most cited work, as far as I know.
Definitely not. Also because it's more recent. Also because okay, in all these issues, there is a very large community. Whenever you go into entropy, information, and so on, community is much larger than the community interested in rigorous mathematical physics.